All right, my people, today we are starting Module 6, which is about circular motion. This is your asynchronous lecture about this topic. So you may know, you probably know that this is one of the first topics that you will be taught that was not covered at all in Sec 5. So I know there's going to be lots of new ideas, new concepts. The new coordinate system is probably the biggest thing. So hang on tight and let's get started. Okay, first of all, I always like to explain the validity of why we do the units we do in mechanics. Of course, circular motion is something that is everywhere. So whether it is actual, things moving in a circle, like say a rock stuck in my bicycle tire. I went out on a bike ride for the first time yesterday. It was wonderful. Or I don't know, sitting on a Ferris wheel and moving around in a circle. Or we can also have things that we approximate as circles, like, for example, the orbit of Earth around the sun, or the orbit of an electron around an atomic nucleus. So, circles, they're everywhere. We use it a lot in physics, and yeah, that's what this module is about, is different examples of circular motion, how to do calculations when things are moving in a circle, that sort of thing. So that's what we're doing. So the first thing I want to define quickly the period of rotation. So the period is just the amount of time that it takes for an object to move around the circle, do one full rotation, or one complete revolution, if that's the case. Kind of prime example is that the Earth takes about 65 days to go around the sun. So that would be its period. To calculate how fast it's going in its orbit, right? We can take the, find the distance it travels is the circumference of the circle. The amount of time it takes is the period. So you can just divide 2 pi r by the period and get the orbital speed, which we'll call it looks like it's uppercase V here. It's, just lowercase v, just speed. One quick note I want to make is that in the textbook, they talk about rotational kinematics, because in normal life, that is a big part of this module. The thing is, that's one of the things that we cut out for the interest of time this semester. So we won't be doing rotational kinematics. So any mention of omega, alpha, calculating things in radians, we're not going to be doing that this semester. Okay, so if I were to identify one key idea of this module is the centripetal acceleration. So it's the acceleration that causes something to move in a circle. So something that's very important is that even if an object is moving around a circle at a constant speed, the centripetal acceleration is always going to be towards the center of the circle. And you can prove that to yourself if you like, right? You could use the motion diagrams and do the subtraction of the arrows. And if you do two velocity vectors that are very close to each other, tangent to the circle, and do that subtraction, then you're going to get the resultant vector is going to point towards the center of the circle. Like, I think there's another diagram in the textbook that illustrates that very well. So even if it's not accelerating around as it goes around the circle, there's still this acceleration towards the center. The magnitude of that acceleration can be found by v squared, so the tangential speed squared divided by the radius of the circle. Okay, so that's centripetal acceleration. You might be like, Miss, well, what about centripetal force? And it's, of course, the centripetal force does cause the centripetal acceleration. The thing is that on your free body diagrams, I don't want you to just label the centripetal force. The centripetal force is always going to be one of the forces that we've dealt with so far in this class. So it might be tension, if you're swinging something around on a string in a circle. It might be the normal force, it might be friction, it might be gravity, right? It's going to be some force that we've talked about so far. again, centripetal force is just whatever force is causing that circular motion, whatever force that's pointing towards the center of the circle. Okay, so don't label it outright. Just label, the forces for what they are. Also, you might be like, I've heard something about a centrifugal force, and that just, if something's moving in a circle, you kind of get swept up in that motion. That's actually just a law of inertia, which is something that we actually don't cover in this course anymore. But know that there's no such thing as a centrifugal force, so we won't talk about that at all, because it doesn't exist. It's just a common misconception. Okay, so this is the tricky part. We are going to use a new coordinate system. So probably in calculus, maybe, even if you're, maybe if you're in Calc 1, but definitely if you're in Calc 2, you know that, the equation of a circle in the xy plane is x squared plus y squared is equal to r squared. So when you have something moving around the circle, a circle, it is moving in both the x and y direction simultaneously, right? It's a curve. So actually calculating the acceleration at x and the acceleration at y separately, and that probably would be really difficult. Okay, so to make our lives easier, we define a new coordinate system, because remember, coordinate systems, we do what we want. Okay, so we define this new coordinate system that we call, the RTZ coordinate system. So R, predictably, is the radius of the circle. So you have to, important part of these problems is to identify where your circle is and point the R axis towards the center of that circle. Then 90 degrees to that tangent to the circle, you're going to have the t-axis. So t in this case is not time. I know it looks like it, but it's not time. It's the tangential axis. Okay, motion tangent to the circle. And then finally, we have the z axis, which is like the x, z and the xy axis. That's the same, right? It's perpendicular to the plane that your circle is in. Okay, so we use this coordinate system because we can see that, okay, if the acceleration is always towards the center of the circle, then it's always going to be in the r direction. So we don't need to split up the acceleration into x, y components. We can just say, oh, the acceleration is in the r direction, and be correct. Okay, so it definitely makes our lives a little bit easier. Okay, so I guess I do break down the three new coordinates a little bit. So radial direction points at the center. So the radial, like the radius in these questions isn't going to change. So we're not doing the type of question where you might have something where, I don't know, you're swinging a rock around your head and lengthening the rope so that the radius gets bigger and bigger. That's quite complicated. You need quite a bit of calculus to be able to do that. So we are just taking the radius to be constant. Okay, so the radius r, the radial position, it's not moving in and out of the circle, so the radial position does not change. The radial velocity is 0 because, again, it's not moving in and out of the circle. But the radial acceleration, we know that in order to move in a circle, there must be an acceleration towards the center of the circle. So the radial acceleration itself is not 0. It's v squared over r towards the center of the circle. If it's moving in a circle, there has to be some force in that direction. Sometimes it's hard to identify, but if there was no force in that direction, it wouldn't be moving in a circle. Okay, next we have the tangential direction. So of course that's tangent to the circle. So that is a variable that could change with time. So we have two options. We have uniform circular motion and non-uniform circular motion. So uniform circular motion is when the object is moving in a circle at a constant speed. So it's moving in a circle at 3 meters per second at every point in its trajectory, not trajectory, but it's in its motion. And so that's constant. Or you could also have non-uniform circular motion, where you do have the object speeding up or slowing down within that circle. So the example of that we're going to look at is what happens if you swing something on a rope in a vertical circle, right? We know that the object is going to be traveling faster at the bottom of the circle and slower as it goes over the top of the circle. So that's a good example of that. We'll do a couple of problems with that. So tangential acceleration, right? That's an example where there is tangential acceleration. If it's uniform motion, we don't have tangential acceleration. And of course, if there is tangential acceleration, there's got to be a force in that direction. So of course, if you're swinging a rock like this, the tangential direction, is tangent to the circle. So that's, in that case, that would be the gravitational force pointing straight down. Okay, so, or some component of gravity that's tangent to the circle at every point. All right, and finally we have Z. Z's not very exciting because we know Z from regular 3D motion, perpendicular to wherever the plane the circle is. Position, velocity, acceleration are always going to be 0 there, right? If it's moving up out of the plane, then we don't have circular motion anymore. Okay, so that means that some of the forces in the Z direction, they always need to cancel. It always needs to be 0 again. Otherwise, it's moving in and out of the circle, so it's not a circular motion problem anymore. All right, I quickly want to mention Newton's law of gravitation, super famous law, super important. We know it at the time, that Fg is equal to mass times the acceleration due to gravity, 9.8. The Newton's law of gravitation is kind of a more general statement about gravity and how it works. So from the last module, right, I know that the force of gravity between like the force of gravity of 1 on 2 is going to be equal to the force of gravity of 2 on 1, right? So Earth's gravity on me is the same as my gravity on Earth. Obviously, it affects me, or sorry, it affects Earth a lot less because my mass is so small compared to Earth. So the more general statement of Newton's law of gravitation is not F equals mg. That's actually a specific case taking, doing the calculation for Earth's surface. In general, we can use this equation. So capital G, which is the universal gravitational constant. So universal gravitational, it means that you can use it anywhere. Okay, so on Earth's surface, on the sun, in any distant planet, galaxy, in deep space, whatever, G is still going to be the same. Then we can multiply that by the mass of one object times the mass of the other object, divided by the radius squared. So, this is a good exercise. So if you take one of the masses to be the mass of Earth, multiply it by capital G, divide by the radius of Earth squared, you actually get lowercase g. That's where the 9.8 comes from. Okay, so the force of gravity decreases with the relationship is inverse squared. So that means, as you move away from the Earth, your gravitational force decreases quite rapidly. So just a note there. So we'll do some examples in class of calculating gravitation like that. Okay, to summarize the things that we've talked about, I've introduced this new coordinate system, RTZ. We'll practice that definitely a lot in class. We have this new force, and we have the centripetal acceleration. We have the centripetal force, which is some force that's causing circular motion. This centripetal acceleration is always going to be towards the center of the circle, and we know its magnitude is v squared over r. Okay, so that kind of sums up the key ideas that you're going to need for this module. In class next week, we are going to be, we're going to be doing examples, really. There'll be a time for you to ask any last minute theory questions you have, and then we'll be looking at different examples of circular motion. So how do you set up that coordinate system when you have circular motion? So have a great weekend, and I'll see you then.